demand function, ordinary demand functions. A consumer's ordinary demand function, sometimes called a Marshallian demand function, gives the quality of a commodity that he will buy as a function of commodity prices and his income. Ordinary demand functions are called simply demand functions unless it is necessary to distinguish them from another type of demand function. They can be derived from the analysis of utility maximization. The first order conditions for maximization consist of three equations in the three unknowns Q1, Q2 and lambda. The demand functions are obtained by solving this system for the unknowns. The solutions for Q1 and Q2 are in terms of the parameters P1, P2 and Y0. The quantity of Q1 or Q2 that the consumer purchases in the general case depends upon the prices of all commodities and his income. As above, assume that the utility function is capital U is equal to small q1 small q2 and the budget constant is y0 minus p1 q1 minus p2 q2 is equal to 0. From this expression, capital V is equal to Q1 Q2 plus lambda parenthesis y0 minus P1 Q0 minus P2 Q2 parenthesis closed, and set its partial derivative equal to 0. Del Q1 V is equal to Q2 minus P1 lambda is equal to 0. Del Q2 V is equal to Q1 minus P2 lambda is equal to 0. Del lambda V, capital V is equal to Y0 minus P1 Q1 minus P2 Q2 is equal to 0. Solving for Q1 and Q2 gives the demand functions. Q1 is equal to Y0 divided by 2P1 and Q2 is equal to Y0 divided by 2P2. The demand functions derived in this fashion are contingent or continued optimizing behavior by the consumer. Given the consumer's income and prices of commodities, the quantities demanded by him can be determined from his demand functions. Of course, these qualities are the same as those obtained directly from the utility function. Substituting y0 is equal to 100 and p1 is equal to 2, p2 is equal to 5 in the demand function gives q1 is equal to 25 and q2 is equal to 10. Two important properties of a demand function can be deduced. Number one is the demand for any commodity is a single valued function of prices and income. And number two is demand functions are homogeneous of degree in prices and income. If all prices and income change in the same proportion, the quantities demanded remain unchanged. The first property follows from a strict quasi-concavity of the utility function, a single maximum and therefore a single commodity combination corresponds to a given set of prices and income. To prove the second property, assume that all prices and income change in the same proportion. The budget constant becomes ky to the power ky0 minus kp1 q1 minus kp2 q2 is equal to 0. Where k is the factor of proportionality, expression 2 becomes capital V is equal to function of q1 q2 plus হচ্ছে lambda parenthesis ky0 minus kp1 q1 minus kp2 q2 parenthesis closed. And the first order conditions are f1 minus lambda kp1 is equal to 0, f2 is equal to lambda kp2 is equal to 0, ky0 minus kp1 q1 minus kp2 q2 is equal to 0. The last equation of 2 to 15 is the partial derivative of capital V with respect to the Lagrange multiplier and can be written as ky naught k parenthesis y naught minus p1 q1 minus p2 q2 is equal to parenthesis close is equal to 0. Notice that these demand functions are a special case in which the demand for each commodity depends only upon its own price and its income. If the utility function were quasi-concave but not strictly quasi-concave, the indifference curve would possess a straight line portions and maxima would not need to be unique. In this case, more than one value of the quantity demanded may correspond to a given price, and the demand relationship is called a demand correspondence rather than the demand function. Since k is not equal to 0, y naught minus p1 q1 minus p2 q2 is equal to 0. Eliminating k from the first two equations of 215 by moving the second terms of the right hand side and dividing the first equation by the second, f1 divided by f2 is equal to p1 divided by p2. The last two equations are the same as 2.7 and 2.10. Therefore, the demand function for a price income set kp1, kp2, ky to the power naught is derived from the same equations as for the price income set p1, p2, y to y naught. It is also very easy to demonstrate that the second order conditions are unaffected. This proves that the demand functions are homogeneous of degree 0 in prices and income. If all prices and all consumers' income are increased in the same proportion, the quantities demanded by the consumer do not change. This implies the relevant and empirically testable restrictions upon the consumer's behavior. It means that he will behave as if he were richer or poorer in terms of real income if desirable for the consumer ceteris paribus. But its benefits are illusory if prices change proportionately. If such proportionate changes leave his behavior unaltered, there is an absence of money illusion. Compensated demand function. Imagine a situation in which some public authority taxes or subsidizes a consumer in such a way as to leave his utility unchanged after a price change. Assume that this is done by providing a lump sum payment that will give the consumer the minimum income necessary to achieve his initial utility level. The consumer's compensated demand functions give the quantities of the commodities that he will buy as functions of commodity prices under these conditions. They are obtained by minimizing the consumer's expenditures subject to the constraint that his utility is at the fixed level U naught. Assume again that the utility function is U is equal to q1 q naught. From this expression, capital Z is equal to p1 q1 plus p2 q2 plus mu u to the capital U naught minus q1 q2 parenthesis closed, and set its partial derivative equal to 0. Capital del q1 capital Z is equal to p1 minus mu q2 is equal to 0. Del q2 capital Z is equal to p2 minus mu q1 is equal to 0. Del mu capital Z is equal to capital U naught minus q1 q2 is equal to 0. Solving for Q1 and Q2 gives the compensated demand functions. Q1 is equal to root over capital U not P2 divided by P1, and Q2 is equal to root over capital U not P1 divided by P2. The reader can easily verify that these functions are homogeneous of degree 0 in prices. The Slutzky equation. If we try to record algebraically the results of previous section, in which the effect of a change in the price of one commodity on its own quantity demanded or on the quantity demanded of another commodity was split up into a substitution effect and an income effect. The result might be as follows: del pi xj is equal to third bracket del pi xj third bracket close plus del pi del xj del pi xj third bracket close m. Since xj is a function of p1 dash pn capital M, the expression on the left hand side is the regular partial derivative of xj with respect to pi. The limit of del xj divided by del pi as del pi approaches 0 and all independent variables other than pi are held constant. The two terms on the right hand side stand for the substitution effect and the income effect respectively. The first of these is not really a partial derivative, since all prices are other than pj are held constant. Capital M is adjusted so as to keep the individual in the same indifference class as before the price change. If we enclose del xg del pi xj in parentheses and appear the letter S for substitution, it should be clear that what we mean. The second term, the income effect, however, is something of monstrosity. It is not really the effect of a price change at all, but rather of a change in the budget equivalent to the change in price in its effect on the consumer's well-being. It is desirable to replace the income effect term as quickly as possible. What then is the change in the budget equivalent to the price change? In figure 18, we could in fact be measured in several different ways, but we are interested in limits as del pi approaches 0, and fortunately in the limit all the measures approaches the same value. We therefore concentrate on the one that appeals most to the intuition. If pi falls by 2 euro, del pi is equal to minus 2 euro, and you have been buying 20 units of xi, you can continue to buy the same amount of everything and have 40 euro left over. 40 euro is then equivalent change in the budget. 40 euro is equal to minus parenthesis minus 2 euro into 20, and in general del m is equal to minus del pi xy, or del pi is equal to minus del capital M divided by xi. Now the original expression del pi xj is of course that part of the limit of del xj divided by del pi that is attributable to the income effect. If del pi is replaced by del m divided by del xi, this part of del xj divided by del pi becomes del xi into del xj divided by del m. As del pi approaches 0, the limit of this expression is x minus xi del xj divided by del capital M, where since xj is a function of p1 comma dash dash pn, del xj divided by del m is a normal partial derivative. Thus, in place of the original unsatisfactory formulation, we have the slutzky equation. Del xj divided by del pi is equal to third bracket del xp del pi xj, third bracket close, s minus xi del m xj.